Hello everyone, welcome to aplusbi. This channel is all about complex numbers, and in this video, which I wasn't able to record as you know on Friday, it didn't publish, so it's kind of delayed, but I wanted to do it on the weekend. Anyways, here we are. We have this problem where z to the fifth power is equal to 1, and we're supposed to evaluate 1 over 1 minus z squared plus 1 over 1 minus z cubed. So based on this equation, based on the values of z, we're going to have to evaluate a rational expression, right? So let's go ahead and do this in two different ways. So for my first method, obviously I'm going to start with the equation. That's what I need to use, right? So since z to the fifth power is equal to 1, that means z is the fifth root of 1, which is basically, we're talking about roots of unity. So if you write 1 as e to the power 2 pi ni, where n is an integer, then from here you get the z values as e to the power 2 pi ni divided by 5. Of course, n can be 0, 1, 2, 3, and 4. That gives you 5 roots, because in the complex world, a number has 5 fifth roots, except for 0, of course. 0 is an exception, okay? Now, what do you do with this, right? For example, what happens if n is equal to 0? Well, if n is equal to 0, you get a trivial case, z equals 1. But that's not interesting, is it? And also it's problematic because z cannot be 1, right? Obviously, if z is 1, we're going to get undefined plus undefined. So we can't do that. So z cannot be 1. So n has to be any one of those values, and that gives you 4 solutions. But does it matter which one, really? It shouldn't, right? Ideally. So let's go ahead and pick one of them. N equals 1 kind of seems the easiest. So let's go ahead and take n equals 1. So z becomes e to the power 2 pi I over 5, right? Or you can write this as e to the power I times 2 pi over 5, which is important because Euler, who is the best mathematician of all times, in my opinion, said e to the I theta, and no one else could say something at this level, okay, something of this magnitude, cosine theta plus I sine theta. So he gave us the most beautiful identity in mathematics. Now, using this identity, obviously, we can turn something exponential into trigonometric along with I. So this is unbelievable, right? Don't you think? So e to the power I times 2 pi over 5 becomes cosine of 2 pi over 5 plus I sine of 2 pi over 5. If you are not familiar with radians, you can easily turn 2 pi over 5 into degrees. If pi corresponds to 180 degrees, pi radians I mean, that would give you 72 degrees, right? And how do you find the cosine of 72 degrees? There are actually really cool ways to do that. And one way is to use an isosceles triangle, which actually includes another triangle, which is similar to itself. So if you take 72 degrees here, 36 and 36, and then you're going to get another 36, okay? And this will give you 108. Now what happens is you do get 72, 72, 36, and another 72, 72, 36. And if you call one of these, I believe this is probably a good one to check. Call this 1, call this x, and then you can kind of do the similarity theorem, so on and so forth. But that's a long story. We're not going to get into that because I don't really need to know what cosine 72 degrees is, okay? I'm going to raise them to powers. So for example, I do need z squared and z to the third power. So what is z squared if this is z, right? Well, if z is equal to e to the power I times 2 pi over 5, then z squared would just be e to the power I times 4 pi over 5. So you just have to double the 72 degrees, which gives you 144 degrees. And z cubed similarly is going to be tripling the angle. It's going to give you 6 pi over 5. And obviously this is greater than pi. So because pi is 180, so this will be, I think, 216 degrees. Something like that. Okay, you get the idea. Now we can go ahead and plug these in. So my expression was 1 over 1 minus z squared plus 1 over 1 minus z cubed. And here, z squared is going to be that, but I want to expand it, obviously 1 minus cosine of 4 pi over 5 plus I sine 4 pi over 5. I'm going to write it that way because I need to simplify it, okay? The exponential form doesn't help. Plus 1 over 1 minus z cubed, which is going to be the same thing, but this time it's just going to be 6 pi over 5. Guess what? We're going to do some trigonometry next. Don't you like that? We're going to be using some double angle formulas. So let me go ahead and show you how that can be done, at least just with this one, so you can hopefully do the other one. We're going to go ahead and use some identities here. And those identities use the double angle, and the rest is going to be similar, okay? The double angle formula basically tells us, for example, cosine of 2 alpha is 1 minus 2 sine squared alpha, or 2 cosine squared alpha minus 1. Which formula would be more appropriate to use here? Obviously, the first one, because we want the 1 to cancel out. So we're going to go ahead and replace the cosine of 4 pi over 5. In this case, we want to use the double angle. So this is the double angle. So alpha, in this case, is going to be 2 pi over 5. So 1 minus cosine 2 alpha, which is 1 minus 2 sine squared alpha, which is 2 pi over 5. Does that make sense? And this will definitely simplify our expression a great deal. And for the sine, we're going to use the double angle. What was the sine 2 alpha formula? That's actually easier because there's only one formula, 2 sine alpha cosine alpha. Sine is nice. So we're going to write this as, because again, 2 pi over 5 is 2 alpha. Alpha will be 2 pi over 5, so it's going to be 2 times sine alpha, which is 2 pi over 5, multiplied by cosine of 2 pi over 5. A lot of work, right? That's why I wanted to do half of it. The rest is yours. When you expand it, one's going to cancel out. We're going to end up with something like this. 1 over 2 sine squared 2 pi over 5 plus, there's going to be actually a minus sign, never mind. We're going to get I times 2 sine 2 pi over 5 times cosine of 2 pi over 5. Now here's what we're going to do. We're going to go ahead and factor out the sine 2 pi over 5 because that's a common factor, actually 2 times that. And when we do, we get something nice. Sine 2 pi over 5 and then minus I times cosine of 2 pi over 5. Now obviously this is going to require a lot of work because now you kind of need to convert it to a form like, okay, cosine theta plus I sine theta. And what is theta? So you can kind of use some reference angles. For this, first of all, you have to switch sine and cosine, and then you want the cosine to be negative. That's going to require some work, but I'm hoping that you can simplify it. And guess what happens at the end? You're going to get a real number and a complex part. And for the complex part, you're going to multiply by the conjugate, simplify, simplify, simplify. But as you can see, this is way too much work, super painful, very brute forcey. You don't want to do that, right? That's what I usually do with my first methods. The first method is like almost impossible to do, right? Well, not necessarily, but it's too cumbersome. So let's go ahead and talk about the more elegant, in my opinion again, method. Z to the 5th power is equal to 1, and I'm supposed to simplify this, right? Now, let's take a look at this. Do we really need Z to the 5th power, or do we need to evaluate Z in this case, right? So let's go ahead and try to make a common denominator. Maybe that's going to help, okay? Or maybe we can try to factor these things. That could also be a good option, right? So, but I'll try the common denominator approach. So multiply by this. And of course, the denominator is going to be a common one, right? Something interesting. This one times this one, okay? Let's simplify this a little bit. 2 minus z cubed minus c squared divided by, now when you distribute this, it's going to be 1, and then you're going to get minus z cubed minus z squared plus z to the 5th. This is the most critical part, and it's just awesome, amazing. Look at this. Don't we know that z to the 5th power is equal to 1? Yes, we do, right? It's given. So you can replace z to the 5th with 1. We have another 1, so the denominator can be simplified. 1 plus 1 is 2, and then the rest, follows. And guess what? The numerator and the denominator are the same. Isn't that mind-blowing? I find it amazing. And now this turns into 1, so the answer is 1. But what happened with the first method? Well, it's super painful, like I said earlier. I'm hoping you're not going to use that at all. And this brings us to the end of this video. Thanks for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe, take care, and bye-bye.